Okay, students. So this lecture will be on sharpness of resonance. The phenomena of resonance, what we discussed in the previous lectures, was for a certain frequency, applied frequency, that is the frequency of the applied external force, either the amplitude or the velocity will become maximum. If the applied frequency is of a certain value, then the amplitude will go to maximum or the velocity will go to maximum. Now we'll study the sharpness of resonance. Now this is going to be very, very important. Let's first deal with the mathematical part of it, and then we'll try to understand it physically. Now what is the power of the oscillation? The power is defined as force into velocity. Now what is the force being applied? The force is F naught. This is the periodic force I started with, F naught e to the power of I omega t. And if you remember the velocity from my previous videos, the velocity was omega F naught by m. This was the velocity term. So I get the F naught square by m. And similarly, what I do is, again I divide the numerator and the denominator by omega. That was done in the velocity resonance. If you remember, I divide this by omega, and if I take omega inside the square root, it becomes omega square. I think I repeated it. So you have the notes with you. You know what to do with this. So again, if I want to take omega square inside the square, I would write omega. So again I would have this term. You remember this for the velocity resonance as well. So this was the velocity resonance term, but now it is power. It is F naught square by m, and this term, this is the amplitude. Remember, this is the amplitude and this is the phase. So I'm not writing the phase every time. I'm not dealing with the phase right now. What I'm dealing with I'm dealing with the amplitude term. So this is the amplitude term. So you can see this is the amplitude term. So this is the amplitude term. This is the amplitude term. Again I want to know, again at resonance, so you see at resonance power must be maximum. That is, at what frequency, applied frequency, the power will be maximum. Now you remember the denominator is same as that of the velocity term. So if you differentiate this and again put it equal to 0, you'll get the same value. And remember, for velocity resonance, you got the frequency at which velocity was maximum was the natural frequency. So the velocity was maximum at when the external frequency was equal to the natural frequency. So even in this case, since the denominator is same function of omega, this is, so the power is also going to be maximum at when the applied frequency is equal to the natural frequency. So when the applied frequency of the force is equal to the natural frequency of the oscillator, the power of the harmonic oscillator is also going to be maximum. So this is the power. So what is the maximum power? So maximum power is when I put omega equal to omega naught. When I put omega equal to omega naught, that is, the applied frequency is equal to omega naught, the power will be maximum. So let us put omega naught. If I put omega naught over here, you will have an omega naught remaining minus omega naught. So this will be 0. You just have 4b squared to the power half. So you have 4b squared to the power half, means it will be 2b. So it is F naught square by m by 2b. That is the maximum power from a forced harmonic oscillator. That is the maximum power. That is the maximum power of the forced harmonic oscillator. Now let us find out the frequencies at which the power will be maximum power by square root of 2. Let us find out why am I doing this. This will be clear as we progress through our lecture. But first let us find out the frequencies at which the power will reduce to P max by root 2. That is the convention that we usually follow. We try to find out the values of frequencies at which the power would reduce to 1 by root 2 of the maximum power. So what is P max? P max is this 1 by root 2. 1 by root 2 is this. So it is 2 root 2 of B. Now what are the frequencies? If we try to find out at what frequencies this will reduce to this value, the power will reduce to this value. I just put, if you see, this is the power, F naught square by m, and this is the denominator. This denominator must be equal to 2 root 2 of B. So for what frequency is omega, this denominator will become 2 root 2 of B. I want to find out the power has reduced. Remember, 1 by root 2 is 0.707. That is, the power is reducing to 70% of the maximum power. So whatever is the maximum power, let us say that the maximum power is 100 watt. Then what are the values of these frequencies for which the power will reduce to 70 watt? 1 by root 2 is 0.707. That is around 70%. So at what frequencies omega, the power is going to reduce to 70% of the maximum power? That is what we are going to trying to find out. So power max by root 2 is nothing but this term. That means F naught square by m is same. F naught square by m is same. That means this term must be equal to 2 root 2 of B. So let us put this term, that is omega naught square by omega minus omega whole square plus 4b square to the power half as 2 root 2 of B. And let us solve this equation for finding out omega. So these will be the values of omega for which the power will reduce to 70% of the maximum value. So let us square it up. If you square both sides, you'll get this term, and this will have 2 root 2 square is 8. You'll have 8b square. So taking 4b square to the other side, you have omega naught square minus omega minus divided by omega minus omega whole square, this term, and 4b square to the other side, you'll have 4b square. So omega naught square minus by omega minus omega, this term, if you take the square root, 4b square root is plus minus 2b. Plus minus 2b. I'll individually take this one by one. First I'll take plus 2b and then I'll take a minus 2b. So taking the first case, that is if it is plus 2b, then this is equal to 2b. So rearranging the terms, you have omega naught square minus omega square is equals to 2b omega. 2b omega. So taking everything to the right hand side, you have omega square plus 2b omega minus omega naught square equal to 0. This is a quadratic equation, and let's solve for the two values of omega. I'll name the two values as 1 and 2. 1 and 2. So omega 1 and 2 is, if you solve this, minus 2b, you'll get this as minus of 2b plus minus square of this, that is 4b square, minus 4ac, a is 1, so minus and minus is plus 4 omega naught square by 2. So these are the two omega values when I take plus 2b. Next I take minus 2b, that is omega naught square by omega minus omega is equal to minus 2b. So again rearranging the terms, that is omega naught square minus omega square minus omega square, omega naught square minus omega square is equals to minus 2b omega. You can see, you multiply omega, you have omega naught square minus omega square minus 2b omega. Take this to the other side, you have omega square minus 2b omega minus omega naught square is equal to 0. And here I name the two roots as 3, 4. So it is minus of minus b, that is plus 2b plus minus 4b square plus 4 omega naught square by 2. You can see this is same, but here there is a minus 2b, there is a plus 2b by 2. So what is the difference between these two omega values? If you subtract this from this term would cancel out, and you have a 2b by 2, that is b, minus minus b, that is b plus b, and that is the shift is omega 3 4 minus omega 1 2, that is delta omega is 2b. This delta omega you will hear specifically in your electronics and communication engineering, you will hear this as the bandwidth. So this is the bandwidth, and that is equal to 2b. You see, that is equal to 2b, and remember, b was the damping. B was related to the damping of the system. B was related to the damping of the system. So what I want to say is, I have drawn a figure. Look at this figure. Look at this figure. This is omega. Remember what was omega? Omega was the frequency of the applied force. And this is the power. The y-axis is the power of the harmonic oscillator. So the power, if you keep on increasing omega, the power increases, and at a particular value omega m, where omega m is definitely equal to omega naught, that is the natural frequency. So whenever the frequency of oscillation, this is the applied frequency, becomes equal to the natural frequency over here, that is omega m, the power is maximum. That is what we found out, that for when omega reaches a particular value, that is the natural frequency, the power of the harmonic oscillator is maximum. And then again, if you increase omega, the power would decrease. So what I want to tell you is, you can see, if this is P max, this is P max, this is P max, then let's say this point is 0.707 of P max, that is P max by root 2 that I was trying to tell. So this is P max by root 2, 70% of P max. This is P max, this is 70% of P max. So 70% of P max has two frequency values. This is omega 12, and this is omega 34. So for these two frequency values, external frequency values, the power of the harmonic oscillator reduces to 70% of the maximum value. So these are the two values between which the power delivered is maximum. If you go beyond these frequencies, lower than this frequency, the power is low. Higher than this frequency, the power is again low. So the maximum power is between these two frequencies. That's why I took 70%. That's the you can say the nomenclature, or this is how you do it. You try to find out the frequencies at which the power is going to reduce to 70% of its maximum value. So definitely, if you want to drive a system externally by applying an external force, you should not apply a frequency below this frequency. Because if you apply the force below this frequency, the power with which the system oscillates will be low. And you should also not apply the frequency greater than this. Because if you apply a frequency greater than this, again the power of the system would be very low. So if you want to deliver maximum power to the system, you need to operate between these two frequencies. Because if you go below this, the power is going to reduce considerably. And if you go above this, the power is again going to reduce considerably. In between these two frequencies, the power of the system is maximum. And these two frequencies, the difference between these two frequencies is called the bandwidth of the system. And this is nothing but also the sharpness of the resonance curve. So this is the resonance. You can see, you increase the frequency, the power increases, reaches the maximum and then decreases. So at a particular frequency, the power is maximum. This is resonance curve. And how sharp is the resonance? How sharp is the resonance depends on this gap. If this gap is low, then this will be a sharp peak. If this gap is wide, then this will be a flat curve. So understand, this I have drawn. You see different curves. This peak, this power curve has a very sharp feature. So the resonance is very sharp. You can see the bandwidth is very low. Again, another graph drawn over here. The bandwidth is this. So it is less sharper than this graph. the bandwidth is large. Again for this one, another one, the bandwidth is still larger and the sharpness is poorer. So you can see that the bandwidth depends on the damping of the system. So if the system has a large damping coefficient B, then the bandwidth is going to be large. In other words, the system will respond to different frequencies. It is not going to be very selective. Please understand the physics of it. It has a very, very beautiful physics. Please understand the physics of it. Say suppose you want to drive a system at a particular frequency. You do not want the power delivered to the system for frequencies beyond that, that is lesser than that or greater than that. You want the system, you want the power of the system to be right at that frequency. That is, you want the circuit or you want the system to be very selective about the frequencies. That is, only if you apply a particular frequency, like in this case, you see this system is very selective about this frequency. If you go little beyond this frequency, little beyond this bandwidth, the power is very low. The system is not responding. But look at this flat curve. Even if you apply, again this curve has also this maxima, but even if you apply this omega, this frequency, the power is considerable. The system is responding even to this frequency. If you apply a frequency lower than this, then even the power is this, a high power. So the system is also responding to this frequency. So this flat system, the system which has a flat curve, is not very selective about frequencies. It is responding to many frequencies. But look at this one, a sharp one. If you go slightly greater than omega, this omega, slightly greater than omega, the power would fall. The system is not responding. If you go slightly lesser than omega, let's say this value, look at this value. If this value, the power is this. For this value, the power is this. See, the power is so low. But for this flat curve, at this value, the power is high. The power is high. So a flat curve, that is for which the damping is high, is not very selective.